All right, everybody, it is time for lesson 2, derivatives of exponential functions. So now that we're hopefully comfortable with exponential functions and logarithms, let's start actually taking the derivative of these things. So we're going to start by determining the derivative of f of x is equal to e to the power of x using the definition of the derivative. So if you recall, the definition of the derivative is that limit we all love, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Everybody's favorite. Okay, but our f of x is e to the power of x, so this becomes f prime of x is equal to the limit as h goes to 0 of e to the x plus h minus e to the x all over h. All right, so what I'm going to do is I'm going to bust out some basic exponent laws here. So e to the x plus h by our basic exponent laws is the same thing as e to the x times e to the h, right? Product rule. Divided by h there. So I can actually factor out an e to the x. And I'm left with e to the h minus 1 all over h. Then I can recognize that since e to the x actually has nothing to do with what h is approaching, e to the x isn't affected by h at all, since it's not affected by h, we don't need to include it in the limit. We can just pull it out. It's not going to change as h changes, so there's no need. It's the same as pulling out a constant, right? Or, sorry, a coefficient. We can do that because it's not affected by the limit. All right, so we're now left with that. So what we want is we want to find the limit as h goes to 0 of e to the h minus 1 over h. Now there's a bunch of delightful calculus tricks that can help us solve that one, but you don't know them yet because they're not covered in this course. So I'm going to go a little bit rudimentary here, and we're going to look at the limit from the left and the right using a table. So we're looking to the limit of e to the h minus 1 all over h from the right-hand side by looking at values of h and comparing it to the value of e to the h minus 1 over h for that value. So we start at 0.1, and then we take a look at 0.01, and then 0.001, slowly approaching 0 from the right. We get 1.0517, dot, 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 1.0050, ellipsis, 1.0005, ellipsis. You see that it's clearly approaching 1. All right, so let's check it from the left, because we know for a limit to exist, we have to check both the left and right-hand sides. So we're going to use negative values this time. So it's going to be negative 0.1, negative 0.01, and negative 0.001. Again, getting closer and closer to 0 from the left-hand side, and we get 0.95165 ellipsis, 0.995016 ellipsis, and 0.99950 ellipsis. All right, so clearly we can see that this limit is also equal to 1. Therefore, the limit as h goes to 0 of e to the h minus 1 over h is also equal to 0. Boom. We got what we needed out of there. Yes, I don't know if you can hear her, but she has decided that now is a good time to complain that I'm not playing with her. All right. So now that we have that, we can see that e to the x times 1 is the answer. Oh, hey, wait a minute. What this means, I'm calling shenanigans. That means the derivative of e to the x is e to the x. Wow. Mind blown. Yeah, seriously, it actually is. The derivative of e to the x is just e to the x. It's nice and simple. Hey, look, it's right there. So the derivative of e to the x with respect to x, anyway, is e to the x. And the derivative with respect to x of e to the u, where u is some function of x, right? It's something else, is just eu du dx. That's just chain rule, right? So we just take the derivative of that interior function u. Okay, so let's try this. Let's see what we can do with this knowledge. So now we're given use the properties of logs and our recently discovered event, that's not right, and our recently discovered result to find the derivative of y is equal to a to the power of x, where a is some number greater than 0. So a is not any complex function, it's just a number, a positive number. That's it. Okay, so here's what I'm going to do. First thing I'm going to do is I'm actually going to take the natural log of both sides. So it's going to be the natural log of y is equal to the natural log of a to the power of x. You might be like, why are you doing this? Just bear with me. Watch what I do, okay? It's going to make sense. So this is the natural log of y. And now by log rules, I can take that exponent on the a and I can pull it out as a coefficient. Well, that's nice. That's convenient. I bet that's going to be useful later. I have this feeling that that's going to be useful. Now, remember before, I mentioned that a neat trick we can do to get rid of natural logs is to just raise everything to the power of, raise everything from e. So this is e to the power of natural log of y is equal to x times the natural, oh, that's not correct, is equal to e to the power of x natural log of a. There we go. That's better. So I raise both sides as powers of e. But we know from before that e to the natural log of something is just that thing because of that inverse operation. Remember, natural log is the log base e of y. So e to the power of log base e of y is just y. But this one, because of that x, I can't really do that trick here yet, but don't worry, it's coming. All right, now I'm going to take the derivative of both sides. So this is going to become dy dx is equal to the derivative of e to the x natural log of a. But we learned how to do the derivative of e to the power of some function, e to the power of u in this case. In this case, our u is x ln a. So we're going to bust out some chain rule here. So we know chain rule for this tells us that d dx of e to the power of u is just equal to e to the power of u du dx. So we just need to follow that rule. So this is going to be e to the x natural log of a times the derivative of x ln a. Okay, well, let's just make sure we know this. d dx of x ln a. Well, think about it. Ln a is just a number. It's not a function, it's just a number, any positive number. Meaning the natural log of a, also just a number. And if I had something like 3x and I wanted the derivative with respect to x, that would just be 3. So the derivative of ln a times x is just going to be the natural log of a, right? Ln a is just a number. So its derivative is really simple. Okay, so that means that I am left with x times e to the power of x ln a. I blame italics for that. She's being very distracting. E to the power of x times ln a times ln a. Whew, that was really hard to say. I hope you made it through the end of that one with me, because that was tricky. All right, now what I can do is I can actually switcheroo this for a second and throw that x back as an exponent of a. And now that I've done that, I can very conveniently say e to the ln a to the power of x is just a to the power of x times the natural log of a. And that's it. That's the derivative for any value of a greater than 0. Hey, look, it's right here. That's so convenient. The derivative of a to the power of x is a to the power of x times the natural log of a. And the derivative of a to the power of u is just a to the power of u. She's literally walking on my computer now, trying to control what I'm teaching. The derivative of a to the power of u is a to the power of u times the natural log of a times du dx. That's just chain rule again. So this is just the chain rule version. Don't forget your chain rule. It's really important. Okay, now that we've got those under our belts, we can jump into some examples. So let's say I've got this puppy. Y is equal to x squared times e to the x. Well, that's a product rule problem right there. So I want to get my f and my g and all that. So f is going to be x squared, meaning f prime is going to be 2x. G is e to the x. G prime is going to be e to the x. Ooh, that one's easy. All right, so this one is actually really straightforward once you get those down. By our product rule, it's going to be f prime, which is 2x e to the x, 2x, sorry, times our g, which is e to the x, there we go, plus our f, which is x squared, times our g prime, which is e to the x. And that's it. We're done. Okay. So again, I got another product rule problem here, so I'm going to be listing some stuff. I've got my f is going to be e to the negative x squared, which means f prime is going to be e to the negative x squared. Well, now I have to multiply by the derivative of the interior, so I'm just going to move it to the front. The derivative of my u, in this case, I keep doing air quotations like you can see me, and you can't, but there were air quotations around that u. And we get negative 2x e to the negative x squared. G we have as sine of 5x, meaning g prime is 5 cos of 5x. Remember, derivative of sine is cosine, then we take the derivative of the interior function, which is just 5. No, my square cut off my exponent. Alas. There we go. So now, take our derivative, dy dx, is going to be, here we go, f prime, which is negative 2x e to the negative x squared, times sine of 5x, that's our g, plus our f prime, which is e to the negative x squared, times 5 times cos of 5x, our g prime. And we done. Hot diggity. Okie doke. This one is not product rule. It's not product rule at all, but it does make use of that new thing we just learned. So if we set our u to negative 6x, again, I won't always do this, but it's the first time doing one like this, so I'm gonna. Du dx is equal to negative 6. Plus, it's really good for you to practice your substitution. We're going to do integration soon. And knowing how to make use of a u and a du dx, that's going to come in handy real soon. So this can be rewritten now as y is equal to 4 to the power of u. So we've got 4 to the power of u, which means dy dx is equal to 4 to the power of u times the natural log of 4 times du dx, the derivative of my u, with respect to x, which means that dy dx is equal to negative 6, the natural log of 4, times 4 to the negative 6x. Just doing my substitution. So just recall that our du dx is the negative 6, and we have u is negative 6x. There we go. Just doing subs back in, and we've got ourselves an answer. Y is equal to 5 to the power of 10x. Dy dx is equal to, okay, so same process. This time I'm going to kind of skip the u du, but that's just because we're going to do it in our heads instead. It's the same process, though. It's going to be 5 to the 10x times the natural log of the base, which in this case is 5, times the derivative of our u, of our exponent, which is secant squared x. See how everything we've done this year is all coming together? We've got derivatives in there. We did some limits earlier. We've got trigonometric functions going on here. It's all involved. It's all there. All right, so Really encourage you to do these tries on your own first and only reference my video if you get stuck. Notice how the answers are on each of these. You're proving each of these. So you can check your answers really easily, but if you get stuck, I am going to go through them. So this one, this gives me dy dx. Take the derivative. That's just going to be e to the power of root x times the derivative of that exponent of root x, which means dy dx is equal to e to the root x times, well, we know that root x is x to the 1/2. So by basic power rule, that's better. That one was better. E to the root x times 1/2 x to the negative 1/2. That was for those of you who get mad every time I say the word power rule without doing the power rule thing, which I know is a very small minority, but it's also a very vocal minority, so I gotta do what I gotta do. Alright, so now that I've got that, I just simplify. This is e to the root x divided by 2 root x. Boom. Proven. Same as above. Word. Okay, B. I am not, nor shall I ever be, cool. But I am really good at making ridiculously large y's that get in the way of my dy dx's. Alright, so this one is, again, a product rule thing I've got going on here. So let's just make note of our f's and g's. So I've got f is x, meaning f prime is 1. I've got g is e to the negative x squared, meaning g prime is going to be, we did this one already. We did this one like a page ago. I'm not even going to go over how I did it. We already did it. It's the same one. I'm not doing it again. All right, so dy dx is going to be 1, that's our f prime, times our g, which is e to the negative x squared, plus our f, which is x, times our g prime, which is negative 2x e to the negative x squared. All right, so that means dy dx is equal to, so what I'm going to do is I'm actually going to factor out an e to the negative x squared. The reason I'm going to do that is because if you look at the answer we're trying to get to, that's outside, so I'm guessing I should factor it out. So I'm going to pull that out of both terms. And if I pull that out, what I'm left with is a 1. And I'm also left with a negative 2x squared, because x times negative 2x is negative 2x squared. And I'm done. Proven. With all my powers. With our powers combined, we are, you guys, you don't know that joke, I'm assuming. See, you don't know that joke and you probably don't care. You should care, just to be clear here. You should care immensely. It's a classic. It's a classic show. Google it. dy dx is equal to, okay, so this is just x to the power of e. That's just power rule. Power rule. It's just power rule. So I'm going to be doing, pull down the e to the front, x to the e minus 1. That's it. I did it. I'm done. I was actually technically done before we started. But just to clarify, it's just power rule. It's just power rule. The biggest reason I included this question is a common mistake students kind of forget at times is remember, e is a constant. E is not a variable, it's not a function, it's just a number. It's just a number. It's a really cool number that does important things, but it's just a number. Okay? E is just a number. Euler's number, just a number. So it follows all the basic rules that ordinary constants do, like 3. E and 3 do the same things. All right. You know what this is. You know what this is. This is quotient rule time. Quotient rule. F is equal to e to the 3x. Did I need to sing that? Yes. 3, e to the 3x is the derivative of e to the 3x. g is equal to e to the x plus 1. G prime then is just e to the x. Because again, plus 1, it's just a constant. Same kind of thing we've always been doing with derivatives. So now I go to do my derivative. I don't know what letter that was supposed to be. Here we go. Again, I don't know what's with me and my y's, but they are getting out of control. So what I've got is I'm going to start with my f prime, 3e to the 3x, times my g, which is e to the x plus 1, minus my f prime, which is, my f, which is e to the 3x, times my g prime, which is e to the x, all over e to the x plus 1 all squared. Beautiful. All right, you might notice that in the thing we're trying to do, the bottom is pretty much the same. It just switched the positions of 1 and e to the x, which we can easily do because addition is commutative. We can switch the order. So what I'm going to do is also note that e to the 3x is on the outside in my solution. So I'm going to factor that out of everything. So this is e to the 3x, and then what I'm left with is 3 times e to the x plus 1 minus e to the x. All over, and I'm just going to switch the order of these right now just to get it out of the way. So hey, the bottom's all taken care of. We just need to simplify the numerator now. So let's take care of the numerator. This is going to be e to the 3x. That's not a 3. It's not a 3 at all. We're going to expand 3e to the x plus 3 minus e to the x. Hey, look at that. That's convenient. 3e to the x minus e to the x. We can simplify that. That's not hard. This is going to be e to the 3x, and then it's just going to be 3 minus 2e to the x, all over 1 plus e to the x. Power of 2. And that's it. We're done. We did it. Lo hicimos. We did it. Da, 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 da. I'm feeling the Door of the Explorer right now. Okay. And that's it. That was the second lesson. Do your homework. Power combined. Do your homework.